This is lab 2, magnetic field of a bar magnet. So for this lab, we had to use a magnetometer and a bar magnet to determine how distance affects the magnetic field of a bar magnet. And then we wanted to calculate the experimental value of the bar magnet's magnetic dipole moment and then create a computational model. So from this, the result was that n is equal to negative 2.8049 and the mu of the magnetic dipole moment is 3.69. So the system for this lab is the bar magnet and the surrounding is everything else. So the lab basically wanted to use the bar magnet, a ruler, and tape to calibrate the magnetometer first, and then we wanted to use a magnetic meter to measure the magnetic field of the bar magnet at different distances, and then use the different distances to calculate the distance dependence. And then based on those, we wanted to create a computational model using the on and a perpendicular axis formulas, and then compare the computational model to the data. So some of the fundamental principles used in this lab is the Biot-Savart law, which basically says that a moving point charge generates a magnetic field, and this is the formula for it that we're going to use in this lab specifically. And then also the distance dependence of the magnetic field of a bar magnet, which is B bar is equal to K R to the N, and then the magnetic dipole formulas for on-axis and per-axis, and superposition, which basically means that the net magnetic field is equal to the sum of the magnetic fields. So some assumptions for this lab is that the bar magnet can be treated as magnetic dipoles, and the only magnetic fields are the Earth and the bar magnet. So these are the observations. So the ones highlighted in greens were the ones that were observed to be true, which was that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. And as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. So this is the data for the measured distances in R. We just filled out the Excel sheet and then created a ln R versus ln Bx graph. So this is how we calculated magnetic dipole moment. So basically, we took the Ln of the B bar equals KRN formula, and then we plugged it into the line of best fit to solve for N, R, and K. And after that, we set it equal to the magnetic dipole moment, which is mu naught over 4 pi equals 2 mu mag divided by R cubed. And then we solved for mu mag, and for this one, we got 3.69. So this is the computational model. So the first one is the mu that we calculated earlier, and then the function calculates the magnetic field using mu and R, and then the bottom 6 vectors creates the observation location vectors, and then the picture on the left creates the arrows for the magnetic field for the on and off axis, and then the d-perp for the picture on the right is the average distance from the perpendicular axis data, and then the bottom creates a magnetic field based on the data, and then the very last picture is what the code outputted. So some possible errors was that when calculating the dipole moment, some mistakes could have been made, which means that the value of the computational model is inaccurate, and also the magnetometer app may have been inaccurate, or there could have been other magnetic fields that we did not account for. So the experimental value we got was 6.23 e to the negative 5 Teslas, and the computational value was 6.73 e to the negative 6 Teslas. So there's a tiny difference. So if we hadn't oriented the magnetic north at north and laid the meter stick out at some intermediate angle with respect to Earth's magnetic field, the values would have been completely different because the magnetic north contributes to the magnetic field measurements. So if it was put at an intermediate angle, the x and y components would be the same because the magnetic north would contribute to both of them evenly. And then so what if we redid the experiment, but instead of using one single magnet, we did two magnets that were stuck together end to end? So the results would be the same, just with a bigger magnitude because the magnets are still pointing in the same direction. So it's basically the same thing as if you have like a stronger magnet.